All right, let's get started. Good afternoon, everyone. Welcome to the Robotics Colloquium. It is my pleasure to introduce Elaine Short. Elaine is an assistant professor at Tufts University. She got her PhD at USC, and she did a postdoc at UT Austin with my advisor, Andrea Tomas. Elaine and I grew up in the HRI community from, baby undergrads to, grad students, and intersected many times. She was a prospective grad student while I was a grad student at Georgia Tech. And then I just remember that when I interviewed at USC, she was the student lead taking me out to student lunch, etc. But most recently, she and I are co-PIs on Access Computing, and I've really enjoyed working with her. Her research is in HRI, different aspects of HRI, and also more recently going towards accessibility. You'll see in the title of her talk. This is pretty recent work, I hear, and I'm really excited to hear.
Great, thank you so much, and thank you all for being here. So I'm going to be talking about human-centered AI for robotics, especially for human-robot interaction, and a little bit about accessibility and assistive technology. But you'll hear in a minute, I think of both of these things as being fairly broad terms. But I want to start us off with a little review, right? We're all roboticists here. We've seen the robot's eye view of the world, right? We have this scene. There are objects in the scene. There are users. And we as a roboticist can look at this and we can think about like, oh yeah, there's like people and stuff happening. But to actually do anything with this, right, we're going to have to go and represent it somehow. So we might take a scene like this. We could represent it, say, as a map. We could represent points of interest on that map. We could have LiDAR scans. We might even have some kind of an occupancy grid to represent where are there obstacles. We can also take the image. We can look at different ways of processing the image, maybe simple processing like optical flow. We could do more complicated processing, maybe some kind of convolutional neural net, and get bounding boxes. We could take a depth image. Often in robotics, right, we like depth images. RGBD is very exciting. We can also represent things about the world, maybe that are a little harder to visualize on a slide, things like audio or motor positions or the forces that are happening on robots, recent actions that the robot has taken. And this is kind of the robot's eye view of the world. But when we package that all up and we talk about something like, say, the state of the world that the robot is dealing with, I want to just take a minute and remember as roboticists that these are numbers. Right? They're numbers in a computer, they're binary numbers. Okay, it's probably actually a lot more numbers than I wrote here, but I didn't have space to do the binary representation of all these different images. And when we put those numbers into the computer, right, the computer can do a few different things with those numbers, right? It can add, the computer can subtract, it can multiply, divide, basic arithmetic. The computer can compare numbers, it can move numbers around, it can read numbers in, and it can send numbers out. And just as a side note, this is actually, right, like wires and gates. And this is basically all a computer can do. Sit with that for a moment, right? And what we're doing as roboticists is we're going to take this and that, and we're going to get this, right? Complicated behavior out of a robotic system. This is a robot at UT Austin. It's a video of the robot picking a block up and putting it in a bowl. And so what we're doing is we're taking the state of the world, we're going to convert it through the fabulous work of many electrical engineers into some kind of numerical representation that's going into the computer. We're going to have a mathematical toolbox for dealing with those numbers. And then we're going to turn it into real-world actions. And everything about this process, other than the little electrons moving around that are the work of physics, is going to be a decision that we as roboticists, as designers, as computer scientists is making. And when we make decisions about how to make things, like a robot, make it do something, we have a name for this. This is design. And this is my core, ethos of how I think about the work that I do, is that algorithm, architecture, and system design are design problems. We can use design thinking. And so we can use techniques like human-centered design to design how these mathematical representations are working on the world. And as a little aside, I want to note that design choices have real-world consequences, right? We have these systems, these AI systems. These are more like not robotics AI, but this is regular, non-robot AI. We'll make decisions about who gets parole, what kind of healthcare are you receiving, who gets hired or not hired, who gets housing, who gets access to mortgages. But also as a disabled person and as a roboticist, right, these consequences can also happen in a robotics disabled person context, right? So this is an example of delivery robots that are blocking people from getting up onto the sidewalk, specifically blocking wheelchair users from getting up onto the sidewalk. And if you think about that as a roboticist, right, you've made some design decisions that are relatively sensible, right? The robot should stop at the curb cut and wait for the crosswalk to be clear before it moves across the street. The problem is a person in a wheelchair looks an awful lot to the robot like an obstacle in the crosswalk. So it'll just stay there on the curb cut. It's being a very good robot. And the curb cut seems like a sensible place to have your robot stop. But then the wheelchair user can't get up onto the curb. So the robot is now making an unsafe situation for a person. And I think I want to highlight here that these design choices and consequences are also not without a broader social context. So that sounds pretty bad, right? Like robot keeping a person from getting onto the sidewalk. But it's actually worse than you think it is, because the existence of curb cuts in most cities is the result of hard work by disabled people and their allies to advocate for the ability to cross the street and get up onto the sidewalks and curbs. So as a roboticist, you're now coming in and taking something away, making a dangerous situation for a community that actually made this cool resource that you as a roboticist are using, which is the accessible city. And many robots are wheeled and use the same kinds of resources that a wheelchair user would use, or a mobility scooter user. So in my lab, backing up, I run the Assistive Agent Behavior and Learning Lab. If you're wondering, did I spend a lot of time thinking about that acronym? The answer is yes, of course. I spent a very long time thinking about my acronym. And we apply human-centered design and what I call here disability community ethics to the development, deployment, and evaluation of AI and machine learning for robotics. So I'm going to talk today a lot about human-in-the-loop learning, human-in-the-loop robot learning, but we also do work on autonomous HRI in groups and other human-human environments. I'm very interested in human environments and human spaces. I am also interested in accessible and disability-friendly assistive robots, although asterisk, again, I think that assistance is something that should be for all people, not just for people who have an officially sanctioned, fully documented disability and so on. And I do a lot of work on accessibility and disability inclusion in robotics and in the computing research community, which Maya mentioned in the lovely introduction. I'm part of Access Computing. So if we're applying human-centered design, what do we mean by human-centered design? So human-centered design, to me, is the practice of designing artifacts, especially engineered artifacts, in a way that takes into account humans, and especially humans as they are, not as we wish they would be. I highly recommend you read The Design of Everyday Things. It's a great book. Everyone should read it. And you should read it, 1, to learn about human-centered design, but 2, you should read about it, because if you've ever walked into a door because you thought it was a push door, but it was actually a pull door, this book will explain to you why that is not your fault, that is the door's fault, or more accurately, the designer of the door's fault. And this approach to designing things means that we should be thinking about testing our designs in the real world with real people, ideally in realistic environments. It tells us that if a design isn't good for people, if people can't use it, that's actually not a good design. And I say this with all the love in my heart for computer science. I am a computer scientist. All my degrees are in computer science. Sometimes we like to talk a little bit too much about user error. And we think of user error as any time the users do something to our system that we didn't predict. And in that case, it's like, oh, the user's messed up. It's not my fault. My system is beautiful and perfect. But actually, what this approach tells us is, okay, no, actually, you just didn't think carefully enough about what people might try and do with your system, and you really should go back to the drawing board on that. And something else I think is exciting about design, as someone who sort of lives in the space between engineering and science, and as someone who's really interested in people and how people think, is that when we do design, and the process of doing design can actually tell us things about how we think about our communities, how we think about technology, how we conceive of our relationship to technology. So that's one half of the philosophical foundations. Oh, and at the bottom here, some papers and some examples. I did not invent human-centered design. I didn't invent human-centered design for AI. I didn't invent it for robotics, including this one of Maya's papers that I particularly like that takes this human-centered approach. On the other side, we have what I call disability ethics, disability community ethics. And you could also think of it as aligned with the social model of disability. I don't give it any of those specific names, mostly because it's really like my lived experience as a disabled person and a member of disability-centered communities. There are specific philosophical traditions associated with some of the more, precise terms for these disability, philosophies or disability ethical frameworks. I'm not too worried about fitting into any of those specific frameworks. I really just mean like kind of a disability-informed way of thinking about problems. And there's a few pieces to this. First, the idea that disability, when we think of disability as a difference in the capability of different human bodies, that's a completely natural part of human variation, and there always have been disabled people, there always will be disabled people, and it's not like ethically wrong for disability to exist, right? But the second piece is that disability in the sense of an inability to participate in some dimension of community life is really more located in inaccessibility, a lack of accommodations, a lack of orienting our communities towards inclusivity than it is, let's say, a problem that exists in the disabled person. And that's sort of basic social model of disability approach. But the other thing that I think starts to get maybe more interesting or more informing of the designs of some of these approaches to robotics is the idea that some of these things that we really value in the disability community, things like accessibility, flexibility, the interdependence of different people, the giving and receiving care, that these are not things that are unique to being disabled, but these are actually things that are about the human experience, and they're things that maybe disabled people have to grapple with a little bit more, like what does it mean to be independent in some sense, but also to receive care? And I think that the disability community has lessons for those ideas in our development of robotics. Sometimes in my lab we joke, although maybe half joke, half serious, that all robotics is assistive robotics. Right? All robots are designed to help people with things, or most robots. I suppose depending on how you feel about entertainment robots. But in general, right, we're designing robots to try and do things. And where they're doing things for people, And what is doing a thing for a person if not assistance? So really like separating, like, oh, there's assistive robots, and that's for the people who really need help. And then there's like regular robots that are for people who also apparently need help, but also somehow that help is different from this help is very weird to me. And I don't like to separate those. I like to kind of keep everything mushed together. And here are some books. I like all of these books. I especially really like Care Work. I highly recommend that one, but Year of the Tiger is also really great. And these are some of the kinds of like works that have informed my thinking in terms of thinking about the disability community. Also participating in projects like Access Computing. All right, so there's some philosophical stuff. But I said we're applying this to robot learning. Okay, so what is robot learning, or how do I think of robot learning? Well, so we have our numbers, right? Like I said, everything the robot's doing is numbers. We can treat these numbers as a function, right? I've drawn this in 3 dimensions because I'm not very good in drawing in like 400 dimensions like most robots have, but this is a very high dimensional space. And we're gonna take those numbers, we're gonna hit them with a function, right? So S bar here is the state, it's this vector, we're gonna take a function, and it's gonna take us somewhere new. It's gonna tell us something about that number, mapping that number to a new number. And often that new number is something like, which of 4 different actions should the robot do? So I have green dots, yellow dots, blue dots, and red dots, and those are the actions that the robot should do. And what we really want this to do, right, is not to tell me for those specific things that I've seen before exactly what I should do. Although often we do also program that into our robots, we want to be a little more general, right? So for these kind of states, you should all do this action. For these kinds of states, you should all do this action. And the thing that I think is really cool as someone who really, really loves math and really, really loves people is that we can ask questions about the nature of this function. Is it probabilistic? Is it deterministic? Is it Gaussian? Is it differentiable? Is it smooth? Right? These are all mathematical properties of these functions. But we can actually go back the other way, back everything out of this, and we're going to get something that the robot's doing that we can describe in words, and we can actually think about, what does that mean for people? Is it predictable? Is it understandable? Is it teachable? Is it even things like annoying? And so this function, when we're actually doing our robot learning, right? So I drew it in 3 dimensions. I said it's very high dimensional. Well, so it might be, an image, right? And even a 128 by 128 image, by the time you start multiplying these things together, we're talking about really long vectors. And when we talk about actions, I've drawn 4 different colors, but of course our robots are making much more complicated decisions than that. Maybe it's a 7-degree of freedom arm, 3-degree of freedom base. We need to know what the face should do. We need to know, I don't know, maybe there's more lights that are blinking, sounds that are happening. So the right behavior here is really, really complicated in practice. So we might like to say, break this down a little bit, right? Rather than just one function that goes from everything that could possibly happen or all these possible inputs to all of these possible behaviors, we might like to break it down into some separate pieces. And this is how I usually think about these problems. So we can look at, what are we modeling about the world? We can ask, what are the possible things the robot can do? We can think about, how much do we want the robot to be thinking ahead versus just trying to do the best thing in the moment? We can ask how the world works. We can think about what behavior is good or not good. And conveniently, we can map these onto different variables. If you are a robotics person, which most of the people in this room are, these should hopefully start to look a little bit familiar. So we can have a set of states, a set of actions, some kind of trade-off between short and long-term decision-making, a function that describes how actions affect the states to give you new states, and some kind of function that tells me like, oh, I did a good thing, or the thing I did had a good effect, or the thing I had a bad effect. And then from this, we're going to get what should the robot do, and what the robot should do is a new function, pi, is a mapping from states to actions, right? We have a state, tells us what to do. This is the same thing as this top picture, right? It's just more complicated, and I've split things out a little bit. I don't know what's happening in this slide. All right, this is a Markov decision process. I think about Markov decision processes a lot when I work. Many roboticists, we get to the point where we sort of like are always envisioning the world in Markov decision processes. We have states, we have actions, we have rewards. Wonderful. So a lot of the work I'm going to be talking about is going to be happening inside of this Markov decision process, but I'm not attached to a particular representation. This actually in practice works quite well for a lot of robotics applications, but to me, I'm interested in this top thing, right? We have some function and we want to think about the nature of the function, the nature of the representations, the nature of the math, and what is it telling us about people. And a Markov decision process, because we have this kind of like idea of rewards, this is a kind of learning called reinforcement learning. Again, this may be a review for a lot of you, but if you're not familiar, reinforcement learning sort of works like this. And it is, in fact, inspired by how humans and animals learn. So in reinforcement learning, we have the world, we have some agents. In this case, the agents are my cats. The world is me and my can of tuna. And there's something happens in the world. There's some state of the world. The agents make a decision, coming over, and maybe the world is a little bit of a softie about their cats and might give the cats a little morsel of tuna. Now, the thing about reinforcement learning is that agents are learning to collect reward, right? And they're learning this mapping from states to actions. And so it's not always going to learn what you expect it to learn. So, for example, suppose I have a can of olives. True story. You open the can of olives, it makes the exact same like pop sound as the can of tuna. And guess what happens? Two cats running into the kitchen, meowing at the top of their lungs. But there's a problem, right? They actually don't get any reinforcement from this because it's olives. I let them sniff the olives. They ask me where I'm hiding the tuna. And they're maybe not reinforced for this. And I think all right, so we can ask, right, this is in some sense, right, the wrong behavior, right? They shouldn't bother coming and running into the kitchen. They should probably keep sleeping on the radiators, which is their favorite thing to do when they're not bothering me to try and get tuna. So we could ask, is this the wrong learning? Is it the wrong model? But actually, you could argue, you could very easily write an MDP, a Markov decision process, that you'd get this behavior out of, because the reality is the reward of getting tuna is so high, it's worth coming and checking it out, right? Like, if it's olives, like, there's no big downside, right? You've maybe left the radiator, and maybe your sister, the other cat, could steal your spot on the best, warmest part of the radiator, but mostly there's really no downside. So, in fact, they're learning the right thing, but they're also not learning the right thing. And so because of this nature of reinforcement learning, that there's no guarantee it's exactly learning what you want it to learn just from the underlying math, we might like to learn with humans, right? So we can have a human, and they can give us some things for our learning problem. We can ask them, either we ask them or they freely offer things like, bad robot, no, don't do that, right? That's maybe some kind of reward or some kind of feedback. We can get examples from people, do this sort of thing, and then you have to figure out how do we actually match that. And this kind of learning both lets us shape what the robot is doing, so it gives us more control over what the robot is doing, but it actually has some other benefits for the robot too, which I want to talk about now. So we've looked at a technique called policy shaping. So in policy shaping, the feedback that you get from the person is to help the robot choose which actions to take while it's exploring what the effects are of the things that it could do. And I quite like policy shaping because it includes some aspect of the environment, right? You're getting some information from the environment, you're getting some information from a user. And when you put those two things together, it's often very powerful. So my student Isaac, for this IRAS paper, was looking at how do we do policy shaping this technique, but do it with continuous actions. So the previous approaches to this had discrete actions. When discrete actions just means you have a selection of a set of things you can choose from, left, right, up, down. Continuous actions are like, what angle do you want? And I can pick any angle, right? I have a dial and I can choose. And the technique he used was to use two neural networks, one learning from the environment, one learning from a person, or actually for a lot of this, a heuristic. This is a COVID era paper, and so the human representation is not so much. And what we found is that comparing to this DDPG approach, which at the time was advanced, although the state of machine learning is moving so fast these days, this is now a little retro, we could in 25 minutes get the same performance as 3.5 hours of training with 6 agents. So your agent hours here in the comparable condition are much more. And in this task, we just have a robot pushing a ball into a corner. This is maybe not the world's most thrilling task, but it is using continuous actions here. So it's not going up, down, left, right. We haven't divided the space into a grid. We're really thinking about the world in a more continuous way. And the slightly tiny learning curve graphs, there are 3 of them, one for this push task, a second for a bipedal walker task, which is a 2-dimensional walking task, BW. And then we also compared against DQN Tamer, another human-in-the-loop learning technique. Each of these has the previous approaches, our approach, and basically we do better in all cases, except for the very last case. You'll see there's a Tamer superhuman graph that does as well as our approach, and that is if you do human-in-the-loop learning with superhuman capabilities for speed and accuracy of feedback, then you can, in fact, do better than less human feedback, like less perfect human feedback, which is not super surprising. And so we see that in this study, we found that human demonstrations, right, including human feedback, dramatically improves performance. I actually think it's important to include human feedback, even if it didn't improve performance on the thing that the roboticist cared about, because it can improve performance on the thing the person cares about. But even that aside, right, even from a pure robotic standpoint, including human feedback can actually improve learning. More recently, we've still been looking at this, but now with some more up-to-date algorithms, although this seems like every 6 months there's a new up-to-date algorithm that we need to test this with. So this is work by my student James, recently published in the Reinforcement Learning Journal associated with the Reinforcement Learning Conference. And he was looking at 2 what are called long horizon tasks. So this means the agent is only getting reward once it solves the problem. In PinPad, it has to enter a pin code. In Memory Maze, it has to find the right hemispheres based on the state. It's looking for a hemisphere that matches the border of the image. And these are tricky learning problems because to get to the point where you get any feedback at all, you basically have to explore randomly until you get lucky. And then once you've gotten lucky once, you're like, I now kind of know how to solve this problem, and you have some hints about what to do. but it's quite difficult in large tasks with large state spaces, right? The state here is the image, so we're learning now from images. It takes a very long time to learn. It takes a long time to converge. And so what James did is he collected a bunch of demonstrations. These are just demonstrations from an expert, which is always code for member of the study team. In this case, it means James. Collected a bunch of demonstrations. And we're really interested in this project and thinking about where do you use those demonstrations? And I'll talk a little bit later about the nature of human feedback and the nature of human demonstrations. But it actually doesn't work as well as you would think it does to exactly imitate what the human is doing. And the reason is because humans are a little inefficient. We're in some ways very good at the task globally, right? We can solve the tasks, and we can solve these very difficult tasks quite effectively. But locally, at each instant in time, on each frame, very rarely is the human making the exact optimal decision. And because of the way these representations work, that can end up actually slowing down your learning. And so what we did instead is we used these demonstrations to train that model of the world, train the world model inside of this Dreamer v3 approach, which is a world model-based reinforcement learning. And by doing that, you're capturing what is important about the world, what are the kind of like good states to be in, but you're not actually directly imitating anything the person is doing. Instead, you then use that world model to train a learning model that is trying to collect as much reward as possible. So overall, this approach, the thing I want you to take away from this is that we're training the world model from demonstrations, not the policy. So we're actually not imitating the choices the person is making. We're just using where the human is taking us as evidence of what is important about the task. And in fact, when we try this on these tasks without demonstrations, you can see up here, it just barely starts learning well after a model that has seen just a little bit of human demonstrations has converged. And we see to some extent this pattern in memory maze, maybe a little bit less strong. We still see this improvement in what is, for a reinforcement learner, a pretty hard problem. And James is currently still working on sort of different techniques for incorporating human feedback and really trying to understand where the best place to use human feedback is. All right, so we're learning with humans. And we might have the human I showed you before, like, oh, the human is giving you the reward, or the human is giving you an action. But actually, that's not what you get from humans, right? You get this kind of thing. Good job. Go left. You're going to knock it over. It's maybe reaching for the cup. Or let me show you what to do. And taking these, right, and squishing them into these little mathematical boxes that we created. This is a reward. This is a positive reward. Or this is an action instruction that implies that this is the right action for this state. Is actually implying things about the nature of this teaching, right? About the nature of the human teaching. And it's applying a bunch of wrong things. Preview, spoiler alert. So one implication of kind of fitting these mathematical formalisms comes up in scalar feedback. So often, if you see interactive reinforcement learning, you'll see people using binary feedback, positive, negative, good, bad. But often, we don't, as humans, use just good, bad feedback, right? We might like to say 4 stars, 5 stars, or A, B, C, D, F. And that feedback is scalar, right? It's on a scale. But the problem with trying to figure out how to use that scalar feedback is, although the scalar feedback often is a number, 4 stars, 5 stars, 90%, 80%, that scalar feedback is not integer feedback. The feedback are not integers. What that means is the distance between 4 stars and 5 stars is not the same as the difference between 2 stars and 3 stars. If they were integers, those distances would be the same. And if you just take a reinforcement learning method that is expecting, say, good and bad feedback, and you say, well, mathematically, there's no reason it has to be -1 or 1. I can, there's no reason I can't just put a number in there. If you put that number in there, it doesn't work. One of my minor gripes with the Tamer paper is they mention that you can do this mathematical operation of putting in scalar feedback. But the approach relies on the assumption that scalar feedback from a human is numeric feedback, and it's really not. Again, if you're a student, perhaps you might know that the difference between an 80% and a 90% is not the same as the difference between a 40% and a 50%, right, in the class. And so what we looked at is we actually went back and looked at scalar feedback. And first we wanted to ask, is there anything here? Maybe we should just be using binary feedback. And we found that actually binary feedback and scalar feedback both seem to have similar potential for learning, but there might be something in the scalar feedback that lets the best teachers be more effective at learning. We also found that although the binary feedback is strictly more consistent, if you allow some differences in feedback, then actually this difference in consistency disappears. And so we wanted to think about, okay, so how do we use this scalar feedback, given that, again, it's not really an integer? And so we developed this algorithm. Sorry, I should have said my student's name. This is Hong Yu, my student, worked on this. And we were thinking about the fact that scalar feedback does actually also give you some other things. Scalar feedback actually makes it easier to detect when your distribution is moving over time, where with binary feedback, you kind of have to wait to see, oh, do I seem to be, is the distribution shifting, or did it just happen to get some good feedback? You have some of that here, but it's a little easier to detect these changes over time. And with our scalar feedback, we can take this scalar feedback, we can convert it into binary feedback, but then we can augment the binary feedback with a confidence. And that confidence now is going to act like a number in the way that the scalar feedback, 0 stars, 5 stars, did not act like a number. It's a little bit related to the same trick that you do when you do statistical comparisons of Likert scale data, which if there are HRI people in the room, maybe you're familiar with this. So we tested this out, and we compared to some different approaches for incorporating this scalar feedback. You might say, well, we can do this sort of adaptive distributions, but why not just do a window or look at the midpoint of the scale? And it turns out that this approach actually works better than any of those. And it does slightly less well than the ceiling performance of an agent with access to everything and that is fully trained. But it starts to get up there in its performance. All right, so I said learning with humans. I mentioned some reasons why I think it's important, but humans are pretty messy. So let's bring back, let's not use real humans, at least to start out with, right? And this is great for robots, right? We can guarantee that the feedback meets our assumptions by generating feedback based on our assumptions. It's great, 100% success rate of meeting our assumptions. The problem is, right, real human feedback is not like this. So my student, Jindan Hong, was asking this question of how do we, if we're going to use this sort of fake feedback generated by what we might call an oracle, a pre-trained model, how can we start to bring that closer to real human teaching? So she did a literature review, and she found in the discussion section of a bunch of reinforcement learning papers that use these oracles, they say things like, well, we use the oracle, but we do note that real human feedback would be more X than this oracle feedback. And we identified a bunch of dimensions that we expect real human feedback would vary from oracle feedback based on that literature review. So we have delay, right? Humans take a little while to make a decision. Frequency, how often the feedback appears. This one actually you do commonly see because even a roboticist has to admit in their heart that humans are not giving you feedback at 100 hertz or whatever your control frequency is. Strictness. So I think we've all had the experience that one teacher's A is another teacher's C. Bias, which is just generally, are you going to get your good feedback? Is the teacher going to tell you if you're doing well, or are they only going to tell you if you're doing badly? And this is a little bit separate from strictness, right? Strictness is how good do you have to be doing well. Bias is how likely are you to hear back if you're doing well versus doing poorly. And then accuracy. Most often, we see accuracy and frequency varied in literature. And we can show that these model parameters meaningfully train the quality of our trained model. So this is a relatively simple learning task. I think this might be taxicab. An AI gym learning task. And we varied these different parameters. We vary the frequency of feedback. We vary the strictness, and especially strictness. A less strict teacher dramatically drops the learning effectiveness. And I suspect, so the smoother degradation with frequency compared to with strictness, I suspect is a function probably both of the kind of information that you get, but actually it also says something about the kind of learning algorithms we've gotten, right? If most of these papers are trying out varying the frequency of feedback, then you're going to design something that's more robust to varying frequency of feedback. We tested this with users, and we had people actually teach a robot, and then we asked people, how do you think you teach a robot? And we've plotted here the values of their real teaching with a vertical line for the standard assumptions, your perfect teaching. And you can see people's accuracy is quite a bit lower. The bias is slightly positive. The strictness is well below 1. And remember, we showed it that in that graph that this is one of the things that really drops performance for some of these approaches, especially for approaches that use the human's feedback to control the policy. Delay was 1 to 1.5 seconds. You can actually look at this compared to information from literature on human physiology. And then the frequency here was close to 1 or sometimes a little less. It's just how often people give feedback. If you ask people, I think the bias is particularly amusing here. So when you ask people, they say, oh yes, I am. Most people say, I'm very fair. Yes, 50-50, equally likely to give you positive or negative feedback. But when we look at people's actual behavior, that's not the case. And almost none of these does the reported behavior match the expected behavior. And while this is for non-experts, I actually think you would see at least this bad and probably worse for roboticists. So roboticists are not immune to this and are likely to make mistakes if you assume what you think the correct accuracy is. All right, so looking at the time, I'm going to talk a little bit more, try and go a little bit faster here. More recently, Jindan has been looking at actual teaching behavior and this question of does the nature of the error, so whether you make a minor error, like, I forget which one this is. I think this is, yeah, a minor error like accidentally putting nothing into your salad when you're supposed to put tomatoes. Or a more catastrophic error, like the robot has decided that you should take the Tide Pod challenge. And we wanted to understand whether that actually affected the kind of feedback, right? Because if you're looking at binary feedback, right, these should both be bad. And that should kind of be it, right? There's the assumption, right, the underlying assumption is that the nature of the error doesn't change the feedback. So we actually looked at a few different kinds of errors, from not adding anything, adding the wrong ingredient, dropping ingredients. And we found that when you ask people to actually teach the robot and you give them a little bit of freedom in what their teaching is, they actually teach differently depending on the presence of an error and what the error is. And so the teaching, the actual teaching, the choices that people make about how to teach the robot are going to change depending on the error. And if your learning approach assumes that people's teaching has to do maybe with the severity of the error, but is going to be basically the same, then you're going to run into problems here. So we might ask, are humans just too noisy? All right, let's fix the problem. No more learning with humans. And I hope you will not be surprised at my answer to this, which is no. And to this, so I mentioned some of the philosophical reasons, right? It lets you know what people actually want, right? Learning from humans helps make sure the robot's behavior is aligned with what the human wants. But it's actually more than that. And we can look to a kind of human-robot interaction. It's called shared control. And in shared control, the human and the robot are controlling a system together. It's nice because the human and the robot are kind of on equal footing here. And it's often used in assistive systems. The idea is that the human is providing some input to the system. The system is going to take into account what the human's feedback is and maybe some additional knowledge that the human system or that the system has about the task. And it's going to clean up the human's behavior to make the user's control more effective. Right? The idea often here is that, say, you have a person who's using a more constrained input device, like a sip and puff, and they're trying to choose between a few goals. If you can just figure out what goal they're going to, you could help them, and right, the robot can take care of this. And so we usually have these assumptions, right, that the user's goals are known to the system, the user's actions are rational, their behavior is stationary relative to the assistance. And we wanted to ask, does this actually hold? So we built the world's worst assistance system. We sometimes jokingly call it the evil claw game. It works like a claw game. You're trying to pick up candy in a cup. And all we did is we told the system the wrong goals. This is a very reasonable error case for shared control, right? If you're trying to infer the user goals and you get it wrong, there's going to be wrong goals. And the sort of assumption is, depending on how you tune your system, that the person, maybe they just keep trying to do what they're doing and they can sort of eventually overcome the system. Or that the system got the goals wrong and that sort of violates our assumptions, so this is just not going to work. And instead, we found that people were not 100% accurate, right? This is a pretty tough system to use, right? It really wants to go to the fake goals. And everything you do, it interprets as evidence for one of those fake goals. But people are mostly actually pretty good at doing this. Not 100%. Yeah, here's someone who's not succeeding at it. They did still get candy. And I think what's really interesting here is that when you ask people about this, they're not saying, oh, I just tried la-di-da-di-da-di-da, I was just doing my thing and the system worked or didn't work. They're actually thinking about what's happening. They're reasoning about how the system works, and they're finding ways to make it work. And the way I think of this, and sort of the difference that I think of this, is in a game theoretic sense, the user always moves last. Right? I get to make my decisions about how I set up the system, At the end of the day, the user is going to use that system, and they're going to use it how they want to use it. And instead of fighting this, my student Isaac, also advertisement, Isaac is on the postdoc market, so if you're in the market for a postdoc, come talk to me, has been thinking about how do we build reinforcement learning systems that think of the user as being intentional and purposeful and helpful to the system. In this case, we were trying to give people control over how the robot was doing a task. So we might have something in the walker case where you could do the speed and the angle. But we looked at this in a painting task. Robot. So this robot is painting a picture, and we trained a model such that people could have control over the pressure and the angle of this robot. And so as the robot is painting, they get to control this. The robot automatically follows the shape, either a heart or we also had a house shape. And when we gave people this system where it's RL trained, but trained to give people control, we found, in fact, that this gives people as much of a sense of control as these shared autonomy approaches, where they really are controlling it. But the performance on the task is as good as an RL model. And it also has this nice property, which shared autonomy doesn't have, that the user can set it and walk away if they want. And I also just want to note, people found ways to express themselves here. So although, yeah, they're tracing a shape and there's only so much you can do with it, people figured out how to both do these sweeping brush strokes where you manipulate pressure and angle at the same time. And they figured out how to make polka dots in the shared autonomy case. So people did find ways to express themselves within this task, even in the sort of constraint. More recently, Isaac has been looking at how do we allow users partial control. And in this case, where a user might control some of the dimensions of a robot's behavior. So, and the approach to do this is we project back into states that we know about if a person takes us out of the states that we know about. A thing about reinforcement learning is that when you're out of distribution, when the agent is in some space that it has never seen before, typically it freaks out. And you can see this here in this very simple one-dimensional example that in your out of distribution case, it goes up, it goes sideways, it just doesn't know what to do. But if we project back into what we've seen before, we can behave in ways that a user expects, and together the user and the system can make things happen. We tested this in a plant watering example. So imagine you have a robot that's trained to carry cups, and you have control over the angle of the wrist. You ought to be able to use this to water your plants, right? We know users will figure things out, they'll try things, and they might try something like this. And by projecting back into known states, we're able to let people much more effectively do this pouring. It works pretty well, at least with this kind of like path following task. In the stop case, so we said, well, okay, maybe the robot should just stop. People figured it out eventually, but they were often surprised the first time the robot stopped. Right? They figured out eventually, like, oh, when it tilts, the robot stops, and they'll figure out eventually how to do it, but they often dumped way too many beads in the first pot. It's beads, by the way, because I said no water by the robot. Our robots are not super watertight. And the RL system does this. You'll see it really fights the user. It just like wanders away. Every time the person tries to pour the beads, the RL agent just goes elsewhere. As you might expect from the videos, this was supported in our subjective data. When we asked people, they actually report the stop condition was not surprising. Like I said, they kind of figured it out, But when you ask people which was more what they expected, then our approach, IOTA, was more aligned with what people expected. And in fact, people were able to, or had lower error, lower is better, in the condition with our approach. All right, so I know I'm pushing the limits on time. So I just want to briefly talk a little bit about the accessibility work. So Kat Allen has been working on makerspaces and makerspace accessibility. It's really important to me to get more disabled people, not just into computing, but also into robotics. And often the way people get into robotics is by going to makerspaces and building things. So we talked to a bunch of disabled makers, and we talked to a bunch of makerspace operators. I think there was not a lot of overlap between those two groups, but we talked to them. And we asked about barriers. We found there are, in fact, a bunch of barriers to accessibility in these spaces. There's a little bit of a vicious cycle of inaccessibility means there's no disabled people, so then there's no incentive to be more accessible. And we came up with some recommendations for makerspaces. There's a lot of text on these slides, but I'm happy to share our insights, or we have a paper at Assets last year about this. I want to mention programs for students. There's students in this room. There's the Tapia Celebration of Diversity in Computing, which is a kind of, I call it like Grace Hopper for the rest of us. So it's a networking and mentoring conference. The CRAWP has the DREW program. There's also the grad cohorts, which for grad students in the room, I highly recommend going to. I did grad cohort when I was a grad student. I found it really helpful. I probably don't need to talk that much about access computing because access computing is run out of the University of Washington. But just note that if you are a student and you do identify as disabled, talk to the access computing people. There are resources available. There's support available. I mentor students regularly. We do mentoring sessions for students who are interested in academic careers. We also have things like conference funding. Access computing also works on institutional transformation. We reach out to other universities. We teach them how to be more accessible. And it's really a great organization. I love access computing, but you all have wonderful access to access computing here, and I won't talk too much about it. So to wrap up, this work is all done by my fantastic students and my postdoc, Ruben. They do all the real work, and are we have yes, and thank you to the NSF, which has sponsored a lot of this work. We have a graduate program in human-robot interaction at Tufts. If you're excited about human-robot interaction, apply to Tufts. We have a master's program and a PhD program. You can email me to join Access Computing, or you could just ask any of the Access Computing people who are in the room right now. I'm also always happy to talk to students or to follow up if you have questions about papers or any of these projects. And check out our lab website and our lab Instagram. And I have left you 3 minutes for questions. Thank you.
Questions for Elaine?
I have a question.
Yeah.
And one thing I didn't quite understand, maybe to do this training or learning or whatever it is, with the robot and the human together, is the human have some partial control of the robot or what, or something like that?
It depends on the project. So in the cases, in the sort of later projects, we do give people partial control. In the earlier ones, we're looking at feedback. So the person is watching the robot and giving feedback. So it really just depends. I guess coming back to this idea of design, right? That's a design choice you can make is like, do you want to give the person partial control? Or are they just supervising? That also has some really interesting like HRI research directions in terms of how does the person feel about the robot? Do people even want direct control? And I actually think that even depends on the nature of the robot, right? Some of our robots feel more like, oh, it's an agent, it's a separate like entity. And some of our robots feel like, oh, that's like my arm. And you don't really want to be like, good arm, bad arm, right? That's a weird interaction to have with your arm. But it's not a weird interaction to have with your robot helper who's going to like fetch things for you. So it just depends on the robot and the interaction.
So for the painting project, could you clarify the differences between like the RL and shared autonomy approach versus just shared autonomy? Because in my mind, both seemed like shared autonomy. I guess I wasn't quite clear how those differ.
Yeah, so we had 3 conditions. We had RL, shared autonomy, and then our approach, which uses these, essentially these sliders, right? These oversight, we call them oversight parameters that you can set that tell you about how you're doing the task. The controls, or the comparison conditions, were shared autonomy, which is a standard shared autonomy algorithm where the robot tries to infer what angle and height a person is trying to get to and tries to help them to that goal. And the RL version, we actually trained 6 different RL algorithms, 6 different RL agents with different combinations of parameters, and people got to pick. And then it just went on its own. So it's sort of like closely controlling the system versus, well, I just pick from one of a set of options, versus now I get to have fine-grained control, but I'm not directly controlling, I'm just saying how it's done. And people liked this as a compromise. And I think it is kind of intuitively how you might want a robot to help you in a lot of cases. Maybe not in the case where the robot is like my arm, but if I'm having the robot do the dishes, I might like to say like, okay, go slowly and carefully. And then once I see it's kind of doing it how I want it, then I want to be able to walk away.
Let's thank Elaine.